The topics I chose for this video are the photoelectric effect and Planck's constant. In this video, I'll describe how they're used in real-world applications and what they are. The photoelectric effect is the observation that many metals emit electrons from light that shines upon it. Electrons emitted in this manner can be called photoelectrons. The phenomenon is commonly studied in physics as well as chemistry. According to the classical electromagnetic theory, this effect can be attributed to the transfer of energy from the light to an electron in the metal. From this perspective, an alteration in either the amplitude or the wavelength of light would induce changes in the rate of emission of electrons from the metal. Furthermore, according to this theory, a sufficiently dim light would be expected to show a lag time between the initial shining of its light and the subsequent emission of an electron. However, the experimental results did not correlate with either of these two predictions made by this theory. Instead, as it turns out, electrons are only dislodged by the photoelectric effect if light reaches or exceeds a threshold frequency, below which no electrons can be emitted from the metal regardless of the amplitude and temporal length of exposure of light. To make a sense of the fact that light can eject electrons even if its intensity is low, Albert Einstein proposed that a beam of light is not a wave propagating through space, but rather a collection of discrete wave packets known as photons, each with energy hf. This shed light on Max Planck's previous discovery of the Planck's relation E equals hf, linking energy E and frequency f as arising from the quantization of energy. The factor h is known as Planck's constant. So to give you more of a visual of what I just explained, let's look to the board here. E equals hv describes the relationship between energy and frequency. E represents energy, h represents Planck's constant, and v is the frequency of the electromagnetic wave. C represents the speed of light, and lambda represents the wavelength. P represents the linear momentum. All these equations were manipulated to find their respective variables. To implement the idea of the photoelectric effect and Planck's constant into real-life examples, we're going to look at solar panels and its relation to the Tesla Powerwall. The company Tesla currently offers two products. The first is the electric car, which I'm sure you know about. The second is the Powerwall. This product's more recent and a lot of people don't know about it. The Tesla Powerwall is essentially a battery for your home. It can collect electricity either from your grid power or for solar panels on your home. It's also clean energy. However, what differentiates it from its competitors is its price point. The Tesla Powerwall is typically about 3 times cheaper than the competitors in the current market. The neat thing about the Powerwall is you can essentially live on your own. That is, if you collect the electricity from the solar panels on your home and store it in the Powerwall, you can be completely off the grid. The opportunities for this in third world countries are incredible. That means remote locations in these countries can live off electricity. To attain this clean energy, you typically have to follow a 4-step process. The first is you have a solar panel that converts the sunlight to direct current electricity. From here, it stems off into the Tesla battery and a power inverter. The power inverter transfers this direct current electricity to alternating current electricity. With alternating current electricity, you're able to use everyday appliances and other electric devices. We will talk about these more later. In direct current, which is known as DC, the electric charge only flows in one direction. Electric charge in alternating current, known as AC, on the other hand, changes direction periodically. The voltage in AC circuits also periodically reverses because the current changes direction. Now that we know the difference between AC and DC currents, let's explore what solar panels are. Today we will be talking about how the Powerwall gets its electricity from solar panels. What we're talking about here is real clean energy. Solar cells convert the sun's energy into electricity. Whether they're adorning your calculator or orbiting our planet on satellites, they rely on the photoelectric effect, the ability of matter to emit electrons when a light is shown on it. Silicon is what is known as a semiconductor, meaning that it shares some of the properties of metals and some of those of an electrical insulator, making it a key ingredient in solar cells. Let's take a closer look at what happens when the sun shines onto a solar cell. Sunlight is composed of minuscule particles called photons. These photons are radiated from the sun. As these photons hit the silicon atoms of the solar cell, they transfer their energy to loose electrons, knocking them clean off the atoms. The photons could be compared to the white ball in a game of pool, which passes on its energy to the colored ball it strikes. Freeing up electrons, however, is only half the work of a solar cell. It then needs to herd these stray electrons into an electric current. This involves creating an electrical imbalance within the cell, which acts a bit like a slope down which the electrons will flow in the same direction. Creating this imbalance is made possible by the internal organization of silicon. Silicon atoms are arranged together in a tightly bound structure. By squeezing small quantities of other elements into this structure, two different types of silicon are created. You have an N-type, which has spare electrons in it, and a P-type, which has missing electrons. This leaves holes in its place, essentially. When these two materials are placed side by side inside a solar cell, the N-type silicon's spare electrons jump over to fill the gaps in the P-type silicon. This means that the N-type silicon becomes positively charged, and the P-type silicon is negatively charged, creating an electric field across the cell. Because silicon is a semiconductor, it can act like an insulator, maintaining this imbalance. Now that we have electricity from the sun using solar panels, we now have this electricity in the form of direct current. We need to change this to alternating current in order to use everyday electronic devices and household appliances. To convert DC to AC, you are going to need a power inverter. Now that you know what a power inverter is, and how solar panels collect electricity from the sun, let's explore what the Tesla Powerwall is, and what it does. Since the Powerwall is essentially a very large lithium-ion battery, let's explore how that works. Batteries store and release energy by moving electrons from one end of the battery to the other. Then we can use the energy from these moving electrons to do work for us, similar to a power drill. These two battery ends are known as electrodes. One is called the anode and the other is called the cathode. Generally, the anode is made from carbon and the cathode from a chemical compound known as a metal oxide. These vary. An example could be cobalt oxide. The final battery ingredient is known as the electrolyte, and it sits between the two electrodes. In the case of lithium-ion batteries, the electrolyte is a salt solution that contains lithium ions, hence the name. When you place the battery in a device, the positively charged lithium ions are attracted to and move towards the cathode. Once it is bombarded with these ions, the cathode becomes more positively charged than the anode, and this attracts negatively charged electrons. As the electrons start moving toward the cathode, we force them to go through our device and use the energy of the electrons flowing toward the cathode to generate power. You can kind of relate this to being like a water wheel and it moving water across a river, except instead of water, we're talking about electrons. Lithium-ion batteries are great because they are rechargeable. When the battery is connected to a charger, the lithium ions move in the opposite direction as before. As they move from the cathode to the anode, the battery is restored for another use. Of course, the fact that the lithium-ion battery is rechargeable makes it more desirable and sustainable, but why else are these batteries so widely used? Lithium-ion batteries are by far the most popular batteries on the market. One of the reasons for this is that the lithium-ion batteries can produce a lot more electrical power per unit of weight than any other batteries. This means that lithium-ion batteries can store the same amount of power as other batteries, but accomplish this in a smaller and lighter package. However, one downside to lithium-ion batteries is that they take much longer to charge than other batteries. And of course, there is always room for improvement in efficiency. This is where nanotechnology comes in. In order to improve the efficiency and decrease the charge time of lithium-ion batteries, many companies and researchers are using nanotechnology to make better materials for their batteries. Hopefully you learned something new from this video, whether it's the photoelectric effect, Planck's constant, solar panels, or how batteries work. Thank you, and I hope you learned something from this video.